Let's see if this is working. I hope it is. 1 second. And there we go. We are live. Okay, so we just stopped in the middle of working on this entity editor. I will just complete it quickly. So all it needs is the concept of an entity object and a plus plus operator as we looked at with iterators. So we'll take a void operator plus plus, which is nothing but, increment. And we will take an entity pointer. So entity pointer current. As you can see, entity iter seems to have an issue, but we can always do a forward declaration for the entity, which allows us to access it from entity iter without having, to have it declared completely. I will also do a few more things, which involves, 1 second, there's an issue with padding. Oh yeah, padding 0. We're not using the flags yet, so this is fine. So I will also start moving all of these into the entity manager.cpp file. That can be done by simply saying move out of class scope and using nice IDE operators to manage all of that. Remove child has become static because it just tries to remove the parent. Interesting as things go, but we will only move it out of class scope. Add child, again, move it out of scope. So now operator plus plus, what will we try to do? We'll just say current. Wait, we can't use it yet. So we'll move definition out of class scope as well. All we'll try to do is we'll take current and we'll try to go to the next one. So next one is entity data also does not have access to entity current. Interesting. Not really, and it's well known why that's happening. So extensions resharper edit, which is generate this for me, getters and setters. So I need the getters for parent. I will need that. And I need next sibling. At least these are required. Inline definition is fine. Return by reference is okay for now. That's a small one. So entity pointer reference is not necessary. So I'll just make it const and return a pointer. Merge the publics. No point actually having separate public and private, multiple separate public and private objects, zones. And we can continue. So coming back, the material entity iterator just needs to take get next sibling. And that is what current becomes. So current equals current next sibling. That's plus plus for us. It has to also return the location. So that's entity reference. And I will return current pointer to current. Say result current. This here becomes entity ampersand. And that should be good. So now what? Entity.children is not existent. I will add it. Void instead will be entity iter. We will return an iterator for the entity children. We will implement this with generate definition. And we will return the entity iter object, which just says current, which is nothing but first child. So M first child. All right. Entity iter needs a begin and an end. How do you get a begin? So entity iter at begin is just nothing but the current. So entity, hold on, begin is the current iterator name. So iter is the begin. It will have to be iterable. So entity iterable, which will give you begin and end. Entity iter is nothing but the iterator for this. Or I can copy that in here, rename this to just iter, right? And this is actually a child iterator, so it's sibling iterator. Entity sibling iterator. Okay. Iterable. That's better. So begin, which will return iterator begin. There'll be end, which returns an iterator end. We need an operator equal to, so Boolean operator equal to the other thing. And we need to define this. So how do we define equal to? We just say other here. So if current equals other dot current, and we return that. All right. Entity iter becomes sibling iterable iterator. So very good stream. Thanks. With 0 views. Ah, man, you have to rub this. Generate definition, begin, return, current. Oh, yours. That's sad. Not in my stream. Just kidding. Entity iterable. I was wondering where you were. What are you doing right now? So I'm making the entities hierarchical. So the parent entity's rotation actually affects the child entities. So this is an iterable that I can return from here. Entity sibling iterable, children. So this becomes again entity sibling iterable. So all I do is I return this, and on the main file here, I can say children, and I can do a for each on this. So I can give for, I can say for entity and child, and I can just go through that children iterable to loop through it, right? For each of these childs, I will draw entity child, and I will pass the world transform in. What needs to happen is this world transform itself needs to be multiplied by the transform of the parent. So this itself is parent multiplied by the thing. That should do the job. Okay. Let's try. Let's see if that is doing anything for us. It failed. Something failed. Let's see. Do we connect dereference and operator if iterate? Dave, that is true because we have not overloaded the percent operator. So we need to overload this one. That is operator, sorry, star operator. First, this generates a definition which returns star current, and that should be fine. Build again. Let's see if this does anything. Failed. What next? What else has failed? Use std function requires template argument list. Specify it explicitly. Build. Does not define a reference to function. Draw entity. Sticks a const entity to get from there. So what is happening? Class does not define an operator. So this is a function type. Draw entity is of a type function. I'll get back to you in a second, yeah? I'm just trying to finish my thinking here first. And I'll get back to you after that. We take XMM matrix and we'll pass the identity matrix here. That seems to do the job. Okay, that worked. Yeah, it was quite nice. No particular like issues or anything, right? There's just, I mean, there wasn't voice, uh, no audio at all. I would suggest at least using one of these YouTube copyright-free music as a background tune. That's it, because the silence can be a little weird for people who listen on headphones with nothing on the background. Otherwise, it was quite good. Okay, where were we? So, what I say is entities. So we were creating this set of entities here. And what I will do is I'll just say that entities like are you have children and parent entities. So I'll take this and set prev. So entity pointer prev equals null pointer. Prev equals this. If append current. If prev, then prev dot add child current. And that should ideally make it so. So that's not working clearly. How do I know? Because add a child should have made it children, which means every subsequent one will be multiplied by the parent's transform, which means they will be increasingly faster at rotation. And they're not doing that. So why is that happening, right? So if not is root continue, and that doesn't seem to get called at all. So we got here, we have an entity. The parent is null, first child, previous sibling, everything is null. Okay. Go next. Ah, I know why. So if prev add a child, and what I did forget is prev equals curl. Otherwise, it's just always going to be null. Okay. What happened here? Old head was null pointer. First child was null pointer. It had no children. So next sibling is null. That is fine. But I'm trying to say null pointer's previous sibling is this. That doesn't work. So here I need to check if old head exists. So if old head, and only then do we actually manipulate old head. Okay, start again. The entity, that is fine. Let's just let it run. Yep. That is similar to what I expected, but absolutely wrong and completely broken. But great tell, do you not find this fun? Okay, okay, okay. What went wrong? So, yeah, this, the entity, we go in there, matrix identity is fine, go in there again, offset, yeah, whatever. But this is just rendering. Parent is identity, so it does nothing. Will transform is a basic rotation, right? So that should render one of them. So that's one. I skipped over drawing it in that. Okay, let's reset. We don't need that one. Okay, so this is one. We go through this, and it never went inside. Okay, second, then this one actually went in inside the children. Go in there. Okay, the draw entity. Go in there again. So now this is hierarchical, right? This is actually going through the hierarchy, going into the children, which is more or less what is expected of this. And it goes deeper and deeper and deeper and deeper. And now it's finishing that nesting. So we're done. So what I'm going to check is entity and is root. So is any of them showing up as not as root? Does that might be a bug? Seems like it, right? It never hits the is root option. So why is that? Entity is root. It is root if M parent is null, right? So if it is not a root, so if it's a child of something, then we continue. Okay. So the question is, why are these entities not root? So come here. This entity has no parents. Completely fine. Second entity. It does not have a parent. It has a first child. Okay. Fine. Come back here. Entity has a first child. No parent, nothing. Okay, continue. Is an entity has a first child. Nothing else. Okay, this seems fishy to me because the first child here, 1F, whatever, it's probably like within the hierarchy, right? Everything is added as a child of another. There should be no objects that are not in this particular hierarchical creation, let's say. So let's just for a second remove the model name. So now everything should be in the hierarchy here. Guaranteed. But none of them are actually showing within that. And that will happen if we forget to set is parent somewhere. Blazingly fishy, wow. It's more like it's so infuriating. I feel like setting this ablaze. Okay. Please don't stop watching. I know I made ton. uh, let's look at parent setting, right? So I do set parent here, or I do add child here. That does nothing but child, and you set parent this. In here, I ensure that the parent is a valid one. Then I actually suggest learning C first. It is harder, yes, but it really gets you into the nitty gritty details, and learning Python after that is very easy. The other way around is difficult, like very difficult. So remove parent works if parent is existent. If it's null, then we don't care. insert self into parent. So m parent equals the parent. Yeah. Parent dot first child is old head. So this should be fine. We call this, right? We called it. Self parent is null. So if m just done, self parent has been set, old head, and parent's first child is this. That returns a child, and the current gets assigned into the previous. Go in again, get a new current, 78670. This is the previous. Previous does exist. We add the child in there and set parent is this. So this is 70, parent is the 600. That is fine. M parent is null, parent exists. So this should be setting parents. This should be correctly setting parents for all the entities. Right? So let's get past it. Let's go to this point and continue. Okay, we've reached there. Now I can check the entity manager state. So entity manager, entities. So there is the first one at the top. Hold on, how many entities are there? 7 entities. Okay, what's inside entities? So this is the first entity. It says the parent, child, all of that, but it seems to be null. Okay. Let's continue through this process. Okay, continue from there. No, that doesn't help us. So we did call set parent, set child correctly, but wasn't where the error came from. Set parent was working. Remove add child worked just fine. Did not remove child in Blaze either. So what gives? Okay, let's look at the iter here. Start. Okay. So set parent. We do have a parent here. We set it. Just fine. Come out here. Entity manager has the base as 520. Prev should also be 520. Prev is 590. Interesting. Create entity manager. Entities. Here is 520. Should be the first one, which has nothing else in it. First one has no prev, so this will be fine. We're going to add a child to it, and then prev will be assigned by curve. Go again. So I equals -1. So this is the third thing in the sequence. Curve was 670 that was assigned to it. $670 here. Prev is 600. Very fishy. Something's pretty wrong with create entity, I think. So let's check what's happening with create entity. That is still a part of create entity. This entity count ++. So that is just going through the entity array. You return entities plus count. That is also correct. Oh no. Oh, that's a bad one. If entity reference dialog equals entity and analog finally. So what's happening here is we incremented the count and then we passed entities plus count. We passed the next one from the one we are actually supposed to use. So everything was off by one. And that is what I expect, right? So the first one is the parent and everything else is a child of the first one. Not the first one, but like everyone else is a child of the subsequent ones. So based on the rotation of the first one, the second one will rotate. So you can see that one. It is also rotating at its own location. And then on top of that, it will have the next one rotating based on itself. So each subsequent one is a further large rotation. So not really. C++ takes a lot of time to fix errors. That is true if you don't pay attention to coding in the first place, right? Like as you saw, like I did the error count by one. I made a mistake there. In Python, this problem would still occur if you do it similar. At the same time, if you do it in a different way where you don't put it inside an array, then fine. Like Python will allow you to just do it and pass it around, but then you don't get to iterate through them at all. If it's in a list and you take the list and you get it from a particular index inside the list, if your index is wrong, it's going to be the same bug. Okay. The transforms are still bad. We're not working properly. I'm making some mistake in the transform multiplication. But that is to do with math, not really with the fact that this is C++. Like, so far, the problems I've faced are less to do with C++ and more to do with the fact that I have made a mistake, like a silly mistake by not paying attention to what I was doing. Okay. So, translation, rotation, and scale. The ordering might be the issue after all. So, parent is perhaps post multiplied because DirectX is a row multiplied system. That seems about right. So the first one is at its base location. I'm going to reduce the number of elements because otherwise it's very chaotic. So minus 1 up to 1 will be easier to see. So the left side is going to operate at a slow pace. Okay, no, that isn't right. That is not at all right. So what happened? First one has a position of -1 in global space. Second one has a position of 0 in global space. And the third one has a position of 1 in global space. No wonder. Of course, it's not working. Because these are, local spaces. These are local spaces. So now everything is 1 unit off from the starting point and things start working a little better. So we'll make them 2 units off from the center and we can start again. Now we can see. So the base one is the one that's slightly on the right side that's spinning in place. The second one is attached to it. It's off by, let's say, it's off by 2 units. So it's rotating on that line at 2 units. And then it's rotating around itself. And the third one is doing the same thing along the second one. And that is correct. So now we've got to a correct entity handling, let's say. So let's uncomment the model and let's comment out. Let's not comment out, but let's remove the child creation. How to create an engine using OpenGL. There are plenty of really good OpenGL tutorials everywhere. They already exist, so I don't see a reason why I should duplicate the thing, I'm not using OpenGL anymore. I'm not interested in using OpenGL either. So don't see a point of doing it. Sorry to say, but like, yeah. My goal here is for me to learn and to make a portfolio for myself. And so making an OpenGL one is kind of distraction, right? As I said explicitly at the start, it's my goal is not to teach. That's what I'm doing. But again, goal is not to teach. There are plenty of these available. Again, for Vulkan, there is one, I think Brendan Galea, who does one. It's quite nice. YouTube, Brendan Galea. Yeah, see? Vulkan, watch on YouTube. So, Vulkan game engine tutorial. It's, I think, still in progress. But yeah, there's a lot of them. There's also this great site called Vulkan Tutorial. But again, start with OpenGL, follow along with text, learn OpenGL because videos are good to listen to. It feels nice, but you don't learn. I don't think you learn as well as you learn from reading simply because it takes you more time and you can go back and forward again and again. With things like graphics programming, which are difficult, like straight up difficult, a video will go through it like 5 minutes. The same thing on text, you'll go again and again, which is much easier. Like not easier, but like much more reliable at making sure you learn. All right, let's get back into model loading. So yesterday when we did the model loading with the original thing, we just tried to get things onto the screen as fast as possible. None of it was built with the idea that we will make something correct. Okay. So we pushed entity using this push entity function that I created without particularly caring how it was being pushed, let's say. So I just took a node and I just quote unquote pushed it, right? Now what I will do is I'll take an entity as a pointer here. This is just a test. Okay. This is just a test I'm doing to see if the hierarchy at least holds. And for each child of the node, I need to add the entity that creates it. So entity pointer int, and we pass that int into push entity. Okay. So this will go in and then it will further add its own children and continue. Here, the int is, null. So we'll pass a null pointer. Oops, null ptr. There we go. And that should be fine. However, when we create this entity, it has to be added as a child of the parent. So I call this parent. So if parent dot equals, or if parent, that much is enough to say, parent dot add child int. Build solution, start. Okay. The rotations have fixed themselves. What hasn't fixed itself is the part where we just add all the vertices to all of them in the entities. So now the question is the vertex counts. When we get the words, we just add it there. We get the transforms from the node. What else does the node have? The node has, well, just that much. Model mesh. So that is there in the node. Words come from the model mesh as well. For the node, so I can say node dot model, so dot mesh vertex count, and I need to take that from the words. So I can say words dot data comma vertex count. What this does is it's a simple, wait, vertex count is also, it's also a vector. I'm going to just assume for a second right there. In reality, I suppose the way it should work is for node dot clear. So size t trim count equals node dot mesh dot vertex count dot size t rem idx equals 0, rem idx less than trim count plus prim idx for each parent, and all of that goes inside. So for each prim idx, we will do this. So we'll take the vertex.data plus node.mesh.vertex start prim idx and vertex count prim idx. What we're saying is we'll take a part of the buffer and we'll just pass that part of the buffer into the entity creation. For each of these, we create an entity. If parent, we will add this child, and this actually goes outside. So end has been created, which is okay. What I will do is I'll take this end outside as well. One step, and vertices will be nothing. This will bug out. I'm very certain this will bug out. Yeah, that bugged out. Because I tried to create a vertex buffer with the size 0. Fine. So this is obviously not going to work. But we've seen the thing rotating more or less. So we should actually just go into the loader function and start working from there. So we'll take the whole words, right? Let's just take all the words, start it. So you can see the orientation has rotated to face away from us. Even if there are two of them and they look a bit wrong, we'll figure that in a second. Okay, let's get back to the important point. So after create entity, we will, what do we have to do? So instead of loading model with this function, I will rename it load model prototype. That's a fake load model, right? The reason I'm only changing its name is because I still want it so that I can check it, refer to it as I go deeper into it. So instead of now doing that load model, I would say load model, and this one's the final one. I don't return a model here anymore. Instead, I take as a pointer entity manager. Okay. I return to you an entity pointer that is loaded from the entity manager. It will be the root of the entity system. Global memory. So what is global memory here? That's whatever the memory we need to use. We are currently allocating on the heap directly for this, so I don't care. We need the textures. Again, we actually will not. We will instead give this thing render device pointer, and it will load the textures itself. Finally, I think that's it. It just needs the file name. So const cast file name. Okay, this is all right. Did I miss a step somewhere? Why did I get render device here? Because it needs to load textures. Why does it need to load textures? Because all our textures are being loaded inside MISC data. Not MISC data, inside entity manager, where it constructs all of these buffers and everything. It loads the texture data here based on whatever texture data is asked for, right? How do we fix the fact that some of these will not provide a texture file? Some of these may not have vertices, right? So instead of taking texture file, first of all, we need to take some material. Instead of constructing that material inside here, it will be provided. So we will go back to Entity Manager. We create a nice little overload for create entities. One where it doesn't take a texture file. Instead, it takes a texture ID. Texture. Okay. Which itself is an easy to construct thing from the material. Texture ID padding, yeah, that does look easy to construct. So instead, it takes a material itself, right? Material. Span of vertices, again, instead it takes a vertex buffer. So we create buffer. No, let me get a span of vertices, right? Okay, what are we trying to do here? Things are a little messed up right now in the architecture because we said we will clean this later and the time has come. Now is the time to clean this. Okay. So we have made assumptions saying that we will create the vertex buffer inside this process here, but we don't have a way of really storing this vertex buffer. We don't want to. We don't want to store all the data related to it. So yeah, we will need a vertex buffer manager, just like a texture manager. So we start with that. Add class vertex buffer manager. Oh, slash. That's necessary. And we don't want to do specializations for vertex buffers. Actually, it'll just be buffer manager. There we go. Come on, please. Please. Okay. So that creates the buffer manager for us. Huzzah. We take texture manager, we copy all of it, and we paste it into the buffer manager. It's a simple way of just getting everything to us without too much work. Now, free list is a thing that we can start extracting, right? It already exists in the other thing. So I will like inside texture manager. So I'll leave it aside. And in texture manager, I will take free list. So free list node and free list. And I will say refactor. Where is it? Refactor. I think I need to do it like this. So refactor. Extract is not an option, but by blaze, add new class, free list, under blaze, simplify under blaze again. Okay. Done. Now we go back, we copy paste the whole free list. Cut and paste it in the H file. Okay. So that gives us the free list that we need. Similarly, the texture manager CPP, which has some free list stuff right there. That needs to include free list, but we have some free list definition somewhere. Free list. Interesting. The definitions are not here. Free list. Other occurrences were not found here. Okay. So let's give me free list.h and see where, okay, this was deleted. All of the rest are inside the H file itself. So let's start moving them out of the class scope. So now freelist.cpp is right there. It doesn't include anything. So we include freelist.h. That makes it a bit simpler. Freelist.cpp. So we take the pushback. There it goes. Push front. There. Pop front. Pop front. There. So it's not paused. Empty. Again. Out of class scope. Begin. Out of class scope. End. the class root again. And we can start nicely closing all of this. This one I have to do it manually, I suppose. Hello. And with the definition, it paste our existing definition right there. Refactoring can be fun. Not. Actually, I'm joking. Refactoring is fun to me. I literally did a thesis on it. All right. So that's free list. That's free list node. We have both of these things. We don't need much else. I will collapse the free list node into the free list itself. So instead of saying node equals this thing, I make it a node. So we don't have a separate type there. This again, Control F, take all the free list nodes, replace it with node. Node. That's it, right? And triggers.cpp will have a similar thing. Again, we just have to do that. Cool. Build solution. Compiling, missing declarations. That is more or less very expected. It asks for a size of free list node. It doesn't have free list, let alone free list node. Use type. Done. Free list node also needs to be there. Free list is added. Things are fine. Texture manager at least should work without a problem. Great. Now buffer manager.h. Again, RID has been duplicated. We wouldn't even use RIDs for buffers. So the buffer here, right? What does a buffer need? What does a buffer have? So it has a VK buffer. It has a VMA allocation. What else does it have? So we can go to entity node. So entity manager, entity mesh. And these are effectively the things we need. We don't need the vertex count. So we don't need that anymore, and we don't need this. So we will have a size to the vertex buffer. Now this, even though it says you're in 32T, it should actually be size T. Because technically speaking, buffers can be sized at anything you want. Free list node, we will need that. So this will actually be free list going to the node, free list going to the node. It says texture. Why does it even know where texture is? Huh? Where can it include it from? So render device doesn't have it. No, render device does have texture manager, but it shouldn't have texture manager included. Like it really should not. Build solution. That worked out fine. Okay, so texture should be incorrect like this. Buffer. Free list needs to be included manually, so include free list. RID texture, we don't care. Offset of buffer index. We don't have indexes in buffers here, so again, don't care. So why don't we have indexes? Because we won't be indexing buffers in shaders. Textures will be indexed, buffers we will not. Buffer manager, so we simply call it buffer manager and everything else remains the same. Index mask and generation mask will stay. Okay. In fact, this is not wrong. We will need an index. My bad. You enter to T index. We will need an index. And so the whole thing that was there before, I will copy it from texture manager again. So after RID, this part, it will have to go back, right? So there we go. Instead of texture, it will now be buffer. And connection might be written over it in invalid state. That is fine. Buffer manager means the user-defined constructor. Yeah. So destroy texture, fetch texture. We don't need those. We don't need that. These valid ID will be useful, but instead of taking a texture ID, it will take a buffer ID. It will say using buffer ID equals texture RID of a buffer. Okay, now it's saying RID needs to be included from a texture manager. Again, RID is not really something that should be in texture manager. So we separate it out. We'll say solution, add new, Blaze, add new class. We call it RID. Let's Blaze RID.h, Blaze RID.cpp. Okay. Templated class. So one of the issues with templated classes is that their definitions are inline, more or less necessarily inline. But we can preload some of these, and we'll see how to do that. So this means RID.cpp doesn't need to exist. I removed it, but it should have been deleted. Control-Z. It doesn't work. All right. Anyway, so RID exists here. Buffer manager.h has an RID. There we go. Texture manager.h needs an RID. There we go. So you can see there's this RID.c. So RID here. Inside texture manager CPP, I can go up to the top and I can say structure RID texture things template structure RID texture, right? What this does is it just says this is added in this translation unit, and in buffer manager, similarly in the buffer manager.cpp, at the top we'll add that. Should be buffer. Okay. And in RID here, we can't exactly do that. So here we'll have to say this external template struct RID texture. Similarly, inside buffer manager.h, and we'll add the same thing for buffer. Don't necessarily need, but I will add it in. Texture becomes buffers. A textures becomes A buffers. Count capacity, we leave them as it is. Render device, all of that are fine. We don't need descriptor sets anymore. Free texture, again, we don't have that. It's a free buffer. Descriptor set layout, we remove that too. Okay, simplified a lot of things. Search and replace with buffer manager instead of texture manager. Buffer manager. 1 second. Okay. All right. Over here we'll take buffers. Cool. So how will we actually give buffers to the GPU? We can bind them like for vertex buffer and index buffer. And for things such as uniform buffers, we can again do a descriptor set manually. However, another way of sending data is through straight pointers, like normal pointers, using a thing known as buffer device address set, which is what we will use. Okay. So buffer device address just gives us a pointer to a given buffer, let's say, and we can just use this pointer as we like. So 2 things we can do. We can actually stop using RIDs for buffers. Instead of a 32-bit RID, we take the buffer and the buffer device address, and we directly provide that. Instead of an RID, we provide the buffer device address. Okay. And then we get it back and go to a hash map to find which buffer it's talking about and then actually execute things on that buffer, right? I'm not certain if that's going to be performant enough. The other option is to take the RID for a buffer, okay? And when it goes to the GPU, we have to change it from RID to something else. And we have to manually ensure that this is done. Same with texture, really. Currently, it's just you just send the RID directly, but later on we will do something like a processing step in the middle to convert the RID to whatever is the banded texture to be sent to the GPU, right? So anyway, for now, I think I'm just going to use this RID and we can fetch the buffer address from the system. Okay, what else would a buffer have? So a buffer will have a byte pointer, so std byte pointer. It's called the map data. So you can write to the buffer through this. We assume the system as rebar SAN enabled. Okay. What is rebar? It's resizable base address register. The idea is that without rebar, you can access maybe 256 MB of your GPU's RAM from the CPU. You write to that, then you move it inside the rest of your GPU RAM, right? Like if you have an 11 gig RAM, VRAM, you copy 256 MB, then you copy into the remaining 11 GB from that location. Okay, so you have to do a CPU to GPU and then a GPU to GPU copy to get anything anywhere. This is what we do for textures. We create a staging buffer on the GPU that is visible to the CPU, copy to the staging buffer, and then from there we copy to the image, which is GPU only. But with rebar or SAN, entirety of your GPU is host visible. It is visible to your CPU. So I can just write, I can just mem copy to the map data. And so we'll use this because it clearly simplifies things for us. Also, it means I don't support anything below 30 series graphics cards from NVIDIA and 6000 series graphic cards from AMD. I do support all the new Intel graphics cards. And we will also need Vulkan buffer device address. So that is UNPTRT. So it's not UNPTRT, it's UN6040. Buffer device. So device address. I was going to call it device address. Okay. All of these will be cached, pre-available to us, so we can just pick it out as we need it. Cool. What else is up? So we have the size. We have an index that we will index to the RID. All of this is okay. No problems. We check the validity of this. Again, it doesn't really exist. We haven't implemented it. So what do we have to do? So we'll go to texture manager and we'll go down to is valid ID. I'm going to copy this and I'll simply directly place this inside the buffer CPP. Texture ID will become buffer ID. Texture manager becomes buffer manager. Const remains const. A textures becomes MA buffers. Everything else remains the same. Okay. So that checks if things are valid or not. Good enough for us, for now, at least. Okay, what is next? So the next is creating a buffer. So let's write the creation function. So inside buffer manager, we say create. Currently, we're only using vertex buffer and a uniform buffer. Let's only do a vertex buffer right now. So buffer ID, create vertex buffer. Okay, what does a vertex buffer need? The vertex buffer needs size, size. What else does a vertex buffer need? Well, we can figure it out when we come to it. So create vertex buffer. Now, that is inside entity manager. For creating meshes, we've said we create buffers. It's in the CPP file. So mesh, this is okay. Material, this is okay. This is like mesh. So we do vertex count, vertex buffer size, buffer create info, allocation info, mem copy. You see, we do the mem copy right there. So I will copy this much and paste it inside our nice little buffer manager class. Start. Whatever, it's the same thing. That mesh dot size is just size now. Okay. Vertex buffer bit is fine. Sharing node is exclusive. Create map bit. This is okay. VMA allocation. Create buffer device address. That doesn't exist. Okay. Most visible bit. We do need that. But allocate device address is not a part of this. It's a part of, what is it a part of? We allocate device. VMA device. It's VK memory allocate device address bit. Okay. Allocate flags. This takes property flags, so that's not the correct one. Does it take property flags anywhere? It does not. Get buffer bit. Whereas right now it's okay. We're not using buffer device address. So this is fine at the moment. But at the end of the day, we will need it. Anyway. Buffers have p-rendered MP-rendered device right there. Vertex buffer, which we will just take like vertex buffer. VK vertex buffer. So VK buffer. VK buffer. Vertex buffer. VK. This will be VMA allocation. Allocation. Right. That's it. We're not actually mem copying anything here. Instead, we will create the buffer. So let's see how we do this in texture manager, right? We create the entire thing until this point, update the descriptor sets, and then we move texture ID. So here is the texture slot creation. Where do we get the texture slot? So we get it up here. So I will copy that much of the I'll copy that much of the code because we will use it inside the buffer manager executed. Okay. So at the top, I'll say we look at the free list. If the free list is not true, we return a malloc. How do you return a malloc? We have to have an optional. We don't right now, so std optional buffer ID. Going there, std optional buffer ID. There's no texture slot, so this is actually buffer slot. Buffer slot. It doesn't matter inside free list because free list itself is type erased. It doesn't care about the type we're using. We can take the render device directly. Okay, so that creates the buffer. Next would be to just initialize the buffer on the slot. So that's here. We need to preserve the index between users as texture does. So we will do that here as well. So many things. So I'll remove that. Dot. There we go. Vertex buffer. Vertex buffer allocation. Map data is allocation info dot map data right there. Device address is allocation info dot device memory. No, what's wrong with you? Okay, we don't have access to device address already. So we'll say 0, size, actually remove device address for now. Size, and index is index that we extracted beforehand. Map data will need a reinterpret task, so we'll do that. Okay, static first, because void pointer can point to anything. That's cannot tell. Okay, now what? So this buffer has been created in a particular texture slot. Buffer slot. Once it has been created, it means the buffer exists at that location, and all we need to do is return the given address, given thing. Oops. Yeah. So what are we? We need to return this that comes from texture manager CDB. What do we do here? Spinner index. We do that in order to write. We don't care about writing anymore. We'll just paste that there. So it becomes buffer item. And as you've seen before, like buffer ID is the same as thing. Cannot convert from unsigned const pointer to buffer ID pointer because index is const. This is why the index was not const in the original one. Cool. We're good for now. Buffer ID has been constructed, it's passed out. It's going to handle itself. Buffer manager has created the buffer vertex. So the detection manager also need to delete it. So let's go to the destroy function here. Destroy texture, which is coming from the free texture function. Okay. So inside buffer manager.h will only do free vertex buffer. Sorry, even a vertex buffer, it's just free buffer. We don't particularly care if it's a vertex buffer or not. So long as it's a buffer, we should be able to get rid of it. Because internally it's just a buffer ID no matter what we do. Generate the free buffer thing and we copy paste it from texture manager again. So do that. Goes there. And texture actually becomes buffer manager. Sorry, buffer. This one with action should be buffer. And now this would be destroy buffer, which will take the given buffer and then fetch texture unchecked again becomes fetch buffer unchecked. And inside texture manager, it will start copying those things as well. So it's texture unchecked and destroy texture. In buffer manager, it's a part of the private thing. So inside the private part, we can add that. Then destroy texture becomes destroy buffer. Texture becomes buffer. Text becomes buff. Buffer ID. Fetch texture uncheck becomes fetch buffer check. Generate destroy buffer. Fetch texture, generate definition. Okay. And now we copy that again from texture manager certificate. Destroy texture. Old code. Copy and paste. The brilliance of Control C, Control V shall never be forgotten. Text becomes buff, image becomes buffer, and the device is asserted any day. Buff.index. Destroy image view doesn't exist. VMA destroy buffer. And text becomes buff. Buffer. dot allocation. There's no extent, there's no format. Instead, buff dot size equals 0. Buff dot map data equals null ptr. Buff dot device address equal. I think I said I'm going to delete device address. So get rid of it for now. There's no format, and index will be added here because we need to increment the generation. So we'll put out any index. In that index, you guarantee to add by the normal stuff. Finally, we push it back onto the free list. Done. Okay, so let's just try the phone. The fetch buffer index is just similar to fetch image index, texture index. You just index into the correct edit. Okay. The solution. Yeah, that deals. So that tracks. However, we don't have a creation function for this yet. So let's write that too. Buffer manager.edge. This is what buffer manager create. We're actually missing a lot. So descriptor set layer. We don't need these inside the function here. Generate definition. Initialize all initialize members. Be render device. A textures. Count is 0. Capacity is capacity. P becomes P render device. Well, A textures is related to A buffers. And if I'm not wrong, so it is A buffers even inside buffer manager. So, yeah. Cool. That handled itself. Destroy. We wish to be destroy itself. So how do we do that? Buffer manager dot so texture manager dot cpp destroy. And we can copy and paste this whole thing. Easy is the set. We don't care about the script set. Okay. Buffers are still allocated, so we check how many buffers are allocated at the end. We reinterpret into buffer. Buffer. Text becomes buff. And what's happening here? So for each member in the free list, we just zero everything out so that we can easily go to the destroy. Buffer, buff, LA buffers, destroy buffer, buff, right? Nothing else. Destroy buffer itself will return if the buffer is not true. Huzzah! So that's simple enough. Okay. So the buffer manager complete. At least as far as I can see, let's check once. There's the destructor that's left, the rate definition. We'll just say it's not valid, just like the destructor here. Right? Assert like this is null. Buffer manager destructor. It's never going to be called, so really speaking, we don't know this right now at all. But perhaps someday the destructor actually gets called. Render device is not initialized but not referenced. How come? They're telling me actually don't do render device in this at all. That's nice. Cool, so that's perfect. And we'll create needs a definition as well. More of the hard part. Dish. So create. There we go. So much stuff, so much stuff. We're going to copy that much, paste it inside the buffer manager as well. But this will be a bit simpler. So buffers, buffer, len, which means the definition, buffer, a line of buffer again. If not buffers, then null pointer, that was fine. We don't need a descriptor set. We don't need a descriptor pool. We don't need a descriptor pool create info. We don't need a descriptor set allocate. We do need that allocation, right? But texture manager gets replaced by buffer manager. Texture manager again gets replaced by buffer manager. If not allocation, again with a null pointer, this becomes buffer manager construction, and all of that goes away. That's all there is. Like, it's not that hard, right? Buffer manager create is much more simple because of buffer device address, which we have deleted. Now, we will need to get the VK buffer out of it. We will need to bind it at some point. So that comes out similar to fetch image review. The fetch image review, we'll have to do that with buffer. So fetch buffer. Free buffer, let's fetch buffer. Buffer. Takes a buffer ID. Definition for it. Oops. The definition is no good because we have a measure here, so I'll be VK buffer. Fetch buffer, and now it's fine. Right? So what does this fetch buffer consist of? Do we actually care? Fetch image here. It's glTF2.0 just that. Fetch buffer inject. This will be that buffer. Does it? No. Tell me more. It doesn't end here. But let's first integrate it into the render device first. So texture manager is right there. We'll add the buffer manager alongside. So buffer manager. Add a forward declaration. Buffer manager. With that line itself. The rest right now doesn't matter. Just inside render device create. We create the texture manager somewhere. Where texture manager is created and assigned until we assert. Do twice. Second one becomes buffer manager. Buffer manager. Buffer manager create. The rest of the formula is exactly the same. Buffer manager pointer. Copy and paste. Oh yeah. Buffer manager failed to enact. And here in this particular case, you want texture manager has to be deleted. Thing is, these are composed, which means render device will take care of it. Even though we are assigning to render device, it's render device's job to delete it. So you can see texture manager is taken and deleted here. Buffer manager will do a similar thing, taken and destroyed. Where solution. Here, run it once. Alright. Close it. Ooh. So now vertex buffers are just IDs. Okay. Vertex buffers are just IDs. Textures are just IDs. And so I should be able to create entities with just IDs in it. So entity manager, entity, mesh. So here the mesh in the entity just needs to contain an ID now. So this will contain buffer ID. That becomes a buffer. Okay, that's mesh right there. Here, this will be buffer. This texture anyway does it. Our IDs will handle the other parts. Let's remove that for a second. So inside create entity, we don't look at vertex buffer size anymore in the mesh. We just instead provide this data down to the size. Semicolon as a whole. Vertex buffer size goes away. Cool. There's a thing. This is device size. So this is actually just size t. And we don't need the whole buffer create info. We just will say then the device dot buffer manager create vertex buffer takes the size, returns this vertex buffer. So mesh dot buffer equals that. Does it? No, it returns an optional. So auto vertex buffer equals this. If not vertex buffer. So if the optional fails, then we return null pointer. Otherwise, we do mesh dot buffer equals std more vertex buffer dot value. Cool. Which means we don't need buffer create info, allocate info, none of that, right? All of that goes away. We do need to write data into it. The way we write data, again, is relatively simple. We just say vertex buffer dot write data. And since we don't have vertex buffer, we need to write it by actually creating a function inside buffer manager for this. So create vertex buffer, this free buffer, this fetch buffer. I will add it here. So void write buffer, write to buffer. I need to take a buffer ID first and RID. We will also take the data. So what format do we take the data in? Take it in void pointer, data, size, t size. But if you're taking it like this, we might as well take a span. So that is exactly what I'm going to do. std span. Now that asks for type anything. I'll say type byte instead. So it's a span of bytes, which doesn't always work very well. Void pointer always seems like the nicest thing to do. Generally, is there a void span? I do wonder. Oops, straight wrong one. Think I've closed the right browser. To prove C++ void span. So we span. So we span with a void point and let's see what happens. So clearly, okay. So void doesn't work. We will take byte. For now, we can just say we take byte, but later on we will template it out perhaps. We'll see. We'll see how we do. So write to buffer. We'll have to first fetch buffer. The naming is a little weird here. So if is valid, write to buffer can return. Write to buffer can return size t. It tell you how much it wrote. It might not write all of it. No. I will add that as a comment. Writes as much of the data as possible. Returns the number of bytes hidden. If it is 0, nothing was written. Okay, that's like the buffer for us. We don't actually like this. Buffers should be written correctly by whoever writes it. So buffers, if not valid, we will return nothing. So this here we can say void, if not valid, RID. Instead of returning null up here, I will actually print out STL log warrant STL category application. Why does it consistent when it buffer is a wallow? Okay. And fetch buffer unchecked. So here we fetch the buffer. Well, actually, I'm just going to assert is valid. Assert is valid. Fetch buffer unchecked. So we fetch it. ID gives us the buffer as a reference. Buffer has the mapped data. What we'll do is we'll mem copy to the map data from data.data with the size of data.bytes, size bytes. So we just copy all of that into the map data. Click and add a const that should be fine. And that writes to the buffer. We will also assert after the buffer is fetched that buffer net size is less than or equal to data.byte size. Otherwise, there's an overwhelming thing. It will say default if you're not careful with this. Ooh, what else is the problem now? What else buffer is nothing under of mesh. Checks out mesh.buffer, right? It's trying to bind that vertex buffer. So it really needs to get this buffer out of the system. How can we do that? Well, just like textures. So for texture, we take it, or we just actually pass it. In case of vertex buffer, we will have to take back the vertex buffer. So we get buffer vertex buffer equals, I need to now get render device or buffer manager dot fetch buffer for the given RID. It returns, if I remember, if I see it correctly, is optional. So I will unwrap it. So value or it's a VK buffer, so it can take a null pointer. So it might return a null pointer here. Okay. Vertex buffer. And I'll say it's only if vertex buffer do we want to bind the vertex buffer. Okay. That's it. We will move this down because until this point, we're just doing position. Then there's vertex buffer. Then there is textures. And then we can continue. So here we draw. We take the first vertex and the vertex count. Everything else is still there. If I run this, it's failed. But if it worked, then running this should work out. Okay, so this is no longer the case. Instead, we want to do mesh. We want to do render device dot buffer manager dot write to buffer mesh dot buffer comma the data which is nothing but vertices dot. So yeah, you can see vertices actually does not work for write to buffer. Because the start span that it wants is different from the start span we're given. So dot data comma vertices dot size. You can then reinterpret cast this. Nope, it's history byte pointer. Okay, that's it. Now what's the issue? Flash is trying to access intermediate function. So just like material, Flash also has to be moved, so it has to be forward Flash through that. Mesh also takes double ampersand references now. Entity also needs to be converted to take double ampersand references. So R value references will be more. Let's see what else. Vertex buffer is not part of the mesh. Yeah, so this again, this goes into render device dot destroy render device dot texture manager, buffer manager, destroy buffer, string. We public one is free buffer. Mesh dot buffer. This is a move. Okay. What else do we have to do? Hmm. I can change that API later. Right now I won't, but later on I can too. Let's just try buffer again. Use this thing about the copy out there. Down, down here in destroy. Again, it becomes this. We will be render device. Pointer out there. Move entity lash that buffer. But then this becomes waved. Allocator is initialized but not referenced because now all of that is handled, all of that is managed by the buffer manager. Succeeded, let's start. It should run, fingers crossed. It did not run. Let's look at it from in the dark. What went wrong? Launch? No. Okay, it did not have automatically captured the page that I asked it to capture. It renders nothing. It never actually goes ahead to render anything. Well, okay. So something failed somewhere in the middle. Is not vertex buffer, but on the point. That looks fine. Does the create vertex buffer fail? Perhaps it is in fact a null. Yeah, it did fail. Why did it fail? Vertices does have a size bytes. Let's go. Okay, we go in. Is free list empty? It is in fact empty because we did not initialize. So texture manager CPP, texture manager, the constructor, and as you can see for the whole capacity, we pass it all into the free list. So buffer manager. We did not do that. So copy paste it there. Buffer and then a buffers, right? So this should work. Nope, no need for that. And that failed. So size bytes is 128, size bytes here is 4. Okay. Oh, wait, that's not going to be the answer of size bytes. Okay. Wait, what? Let's do this. So buffer size is says 128. So if I go into data, hold on. Think I know where the issue is coming from. It's from the right use of right to buffer. I think I just made a mistake when I used it. So it writes here. It's what I suggest size, or what I suggest size bytes, right? What I will do here instead of asking for a span of, because you're asking for a span of known type, I will go to this one. I'll copy it, paste it again. This time I take a type T, template, type name T. Now this is templated. It will take any spans. And this right to buffer that actually takes a raw span goes here, where we can change it from taking a raw span to something else. Like, for example, word pointer data followed by size, T size. Now, since this is a templated version, we'll have to write it in the declaration itself, but it's not going to be that difficult. It will just rely on right to buffer, take the RID, data.data, and data.size bytes. And now this is a generalized, right? Generate a definition for this in there. There is another right to buffer somewhere. Span, it's right here. We cut this, do that, go back to this one, and we'll type it there. So there's no data.size bytes. It's literally just this size. And we copy from a given data for a given size. And we don't care about the rest. Since it is an internal one, I will also change the name of this one. Rename this overload IMPL. All right. So that should handle it for us. Like to offer IMPL. Thank you. Inside there, it's also IMPL. Data becomes const, size becomes const, no problems. Build. And now I can just pass the entire vertices array here. So vertices, and it will just work. Start. Okay. The bot has been called. So what happened? Some allocations were not freed. This was memory block getting destroyed. Comes as a part of an allocator here. So that does not track for me. Because buffer manager.destroy should have destroyed all of the buffers, right? If we had forgotten to create to delete a buffer, that is. M count is 0. So this has to have been freed. Let's look at destroy buffer to see what was happening. Restart again. Close it. If I went to destroy buffer, but the count here is still 0. How is that possible, right? So create buffer. So that creates the buffer here. takes one from this. Never incremented the count. Texture manager, where do we increment the count? Create texture. So it allocates it from this. And at the end, never actually increase the count even in this type. That's sad. It's not a big deal. It doesn't, like, we don't actually use it for anything other than those asserts. But yeah, it is sad. So texture slot, and we will count plus plus and count plus plus. Okay. Similarly in buffer manager, if we have a buffer slot, plus plus count. Okay. Inside destroy buffer, once it's destroyed, we will say minus minus m count. And this will be similar in texture manager.cpp. Destroy texture at the end, m count. Okay. Then it will still fail when I delete it. But at least it will try to destroy the buffer. So the buffer is null, this one continues. Buffer is null, this one continues. Buffer is null, this one continues. Our bot has been called. Retry. Memory, wait, data is released. Okay. How did that happen? Let's keep this through buffer manager.cpp. Instead of destroy buffer, let's look at destroy. So destroy. And I can put a point here. I would run it. Close. What was the count? The count was 3. So 3 have been allocated, which have not been freed. So that's interesting. Inside buffer, so free buffer, which goes here, goes inside for destroying the buffer, and we do reduce the count, which means we literally have now called destroy buffer in this. Okay, that is understandable. That is the whole freeing procedure. We don't care about that. There we go. So it takes the buff, which is null. A buffer seriously, it's just null all the way. About. So that doesn't make any sense. So entity manager, let's look at the mesh. So mesh is here. Material moves into there. Inside entity destroy. So let's swap destroy entity here. We free the texture, we free the buffer. All of them are done. Both of them are done. The freeing buffer goes there. When we destroy buffer, which does reduce the count. But if the buffer is null, then that doesn't work. Okay, let's check what's happening there. Those about 3 buffers still allocated, 3 textures still allocated. Neither the textures nor the textures seem to be deleted. Totally sounds like a bug to me. But we need to debug further. So here we do text.image, right? Destroy entity does free these things, at least tries to. So along with this, do we even call destroy entities? Okay, we do call destroy entities. So for entity of material, let's do something like that. It's just a Now in material A. Why is the material null? We will destroy entity. So the entity is in it, right? Like it definitely is in it. We destroy the sampler. So sampling in the material is null. That is expected. But the texture index is also zero. So texture was null. Similarly, buffer entity mesh, the buffer is zero. So this entity that is being destroyed here is actually a zero entity. Step out. So it's for each entity in the entire thing, we just do a delete. Okay, that makes sense. Suppose. So the entity is something we never explicitly tried to destroy. Go in there, capacity is 10, entities is 0. Not 0, but like it has some value to it. Iter equals entities. So we got iter, which has null things for parent, child, and everything. But the mesh is like actually has an index and has a vertex. So great. Go to destroy entity. We check if the entity is a thing. Step. Entity is in fact a thing. If it's not in it, then we return. But it was supposed to be in it. So that means it's not in it as now is some issue. So it sees buffer or action. First of all, I'll call it no. Isn't it like this? Second of the debug pointer, run it. Was okay, it's the second one, we can ignore it, continue. Alright. So what's happening? Entity has a mesh, which has a buffer. Okay, buffer has a value. Material has a texture has a value. So what that means is it's not telling me, hey Kazir, it's telling me that my init somewhere the boolean one conditions are for wrong. So inside buffer ID, RID is a boolean cast. Return if index equals 0, right? So boolean false doesn't check if it's invalid, it just checks if it is equal to 0. That is fine because it will be 0 if it's invalid most of the times. The big deal is it's supposed to be not equal 0. It's boolean. It's trying to see if this, so if it do, it should evaluate true or not. It should evaluate true when index is not equal to 0. Now it should be able to delete things properly. So is in it? Yes. Now it actually deletes things. Right? So I can continue. And I deleted just fine. Everything closed just fine. There we go. Okay. So entities are, let's say, well settled in along with buffer manager. Time to get data to node from memory loader itself. All right. How do we do that? So I'm going to design this today. I won't implement the whole thing because not enough time. And the design itself is going to, let's say, be a bit long. So let's start melting. Oh, so that's the old one, huh? So it's the explanation for the entity hierarchy. Okay. Where did my pen? Give me 1 second. All right. So effectively, what we're trying to do is we're trying to load the entire scene, right? Each model in glTF has a given set of mesh nodes, right? Which is going to be like your hierarchy. So there's going to be like nodes on top of nodes on top of nodes, right? And each node can have a mesh, not men, have a mesh. It's E for array. So it can have a mesh, may or may not have a mesh, right? And each mesh is nothing but a set of primitives. And these primitives contain a vertex start, so vertex start, as well as a vertex cut. Why do you need a vertex start? It's because you don't want to have a vertex buffer per primitive. That is very inefficient. Instead, you want a single vertex buffer at the level of a model. So vertex buffer here, which contains every piece of data. Then here you will say something like mesh index. And then inside this particular sub allocation, which is the mesh index, you will further go for a primitive index. So primitive start, let's say. So this is the sort of construction we want. So all the vertices for the entire model may be collected into a single big vertex buffer. And in reality, what we will end up doing by the end is every single bit of the world will be inside a same single vertex buffer. Oops. 1 second, yeah. So every single bit will be inside the same vertex buffer. And then you will say model ID here. So like model IDX, right? So based on that, we want to lay things out. Now, if we look at what I've done already, so if you take load model, for example, so load model prototype, as we call it, we load the buffers over that is fine. We just take a vector of nodes and we're just like parsing every single node without caring about anything else. What we will instead do is we'll take positions as a thing of its own, and then each attribute separately, we will consume them as a thing of its own. We'll assign all of them into the array, and each primitive will be assigned the given vertex offset. So all of that will be set up. What is missing is how do we show the primitives in the system? So each primitive uses the exact same transforms as the mesh. Each mesh uses the same transform as the node. So having more transforms for on a per primitive basis is useless. It's going to waste a lot of space, and we don't want to do that. At the same time, on a per mesh basis, having multiple primitives is going to cause us like a lot of effort, let's say. So the way to go would probably be to say that each entity has a primitive, right? It can have a primitive. And we create the hierarchy such that some entities can be models, so model roots, let's say, while others can be mesh roots. That, of course, wastes some things with respect to materials, because not everything, only the primitives will have materials. And similarly, vertex offset and all of that data will also be only restricted to the primitives, while everything else will be a pure set of transfers. Meshes, so if you look at the noding here, process node, process mesh. So if you go to process mesh, each mesh is just a collection of primitives. So if you go to the glTF mesh, ignore this. It's a collection of primitives. It has a name, it has a collection of primitives, and it's got a collection of weights and targets. That's for animation. Okay. Right now, we only care to look at the primitives themselves and how do we handle that with animations at some point. So with animations, we will change the transforms for the given mesh. So we add something like an animation bound animation element to it, I suppose. Uh, I think I will end here. The design will take a bit of thinking time, and I don't want to just hook along people while I think. So tomorrow I'll start coding the particular system here for the primitives and everything. All right. It's nice having you. Have a good time. Enjoy. And see you.